Hello all, I welcome you all to the 25th lecture and the last lecture of this course E614. We will finish the course with a short session on heterojunctions. That is something that we did not uh, discuss during the course of this lectures. So we will briefly touch upon heterojunctions. We will not go into much further detail because it's beyond the scope of this lecture series. And finally, we will spend some time to summarize and conclude on what we have learnt till now. So, till now, we discussed mainly about uh, homojunctions in the sense that you have P and N from the same material system, and mostly we have discussed only about silicon. Most of the problems we have done are based on silicon. We assumed a lot of things based on silicon. So you can have an heterojunction if the two materials which join, it can be P, it can be N, of these things that we typically saw, is it's a junction between two dissimilar materials. An example of a heterojunction is also silicon dioxide. This is something that we saw, but it is also an heterojunction, but it is not very interesting because silicon dioxide is typically a very bad conductor with a very large band gap, right? So basically it does not give us any interesting information. Other heterojunctions of interest are gallium arsenide, aluminum gallium arsenide, indium phosphide, uh, indium gallium arsenide, gallium phosphide, gallium nitride, aluminum gallium nitride, and all these guys are all heterojunctions because they are grown on the interfaces of two different materials are actually uh, realized by growing one on top of the other, right? So typically they have different band gaps, and it is very hard to randomly align each one of them because there exists a relationship between the band gap and what is called as a lattice parameter. This is a very crucial aspect in any heterojunction. So I am plotting the band gap versus lattice constant, okay, some A which is in angstroms. Silicon has, so basically let me write this as some 1.2 eV, this is 2.4. Silicon is among the smallest lattice element, having the band gap of about 1.16. Gallium arsenide has a smaller band gap but a larger lattice constant. Sorry, germanium smaller band gap, larger lattice constant. Gallium arsenide is something which is very similar to germanium but has a larger band gap. And on top of gallium arsenide, if you replace gallium by an aluminum, you get a series of materials which are called algas, and at the end you have aluminum arsenide. Any of these things in between is aluminum gallium arsenide. You have replaced few gallium in the gallium arsenide crystal by aluminum, you get what is called as aluminum gallium arsenide. Gallium phosphide has a much smaller lattice constant but a larger band gap, and you have what is called as, if you replace gallium arsenide, gallium and gallium arsenide by indium, you have what is called as indium arsenide, and anything in between is indium gallium arsenide and indium phosphide lies here, right? So anything in this is indium gallium phosphide. So the lattice matching, which is typically said, is that if you have similar lattice constant, if I draw a line between two materials and they fall on similar on or very close x values, they are called as lattice matched. So basically, gallium arsenide and aluminum gallium arsenide, so this line is very well lattice matched because they fall on the same line, so the lattice constants are very similar. So you can grow gallium arsenide and continue growing aluminum gallium arsenide of any percentage of aluminum and gallium. So you can have aluminum 0.2, gallium 0.8 arsenide, right? Aluminum 0.3, gallium 0.7 arsenide. All these guys are called gases, right? Now, why would anybody want to do something like this? The reason behind this is to have some dissimilarity between these two junctions, and we will very soon see why you need such dissimilarities. But before we go there, we have to see what happens if I join these two. To study that, so basically we saw that the materials have different band gaps. The materials also have different electron affinities. So what we mean by that is that, let's say we have two material with energy 1 and another one with energy 2. So these two can be aligned in this particular fashion, right? Or it can be with this fashion, same with Eg2, or it can be in this fashion, same Eg2, right? So it depends on the electron affinity. This is chi1, this is chi2, and this is chi3. Right? So depending upon the electron affinity, you have three different types of band alignments. The first band alignment where it is like this, right? This is called as type 1 heterojunction or straddling heterojunction. The second one where you have something like this, right? This is called as type 2 or staggered. And the third one this is called as type 3 or broken gap heterojunction. It's pretty self-explanatory why each one is called such, right? So now let us look at one particular situation as to what happens when these two materials join each other, right? So of course the type of band structure or heterojunction which is formed depends upon the electron affinity, right? If one electron affinity is similar to the other one, you mostly get straddling. If you have one slightly away from the other, you get type 2. If you have one very largely away from the other, you get the broken gap, which is obvious from these diagrams. Now let's see what happens to the current and how the bands align each other and what are the special features when we have heterojunctions. So let us consider the first material here to be an n-type semiconductor. So we have the Fermi level here, EF1, this is EC1, this is EV1, and the vacuum level. And as we have done previously, this is written as Q psi S1. This is the work function of this particular material. And this is Q chi1. This is the electron affinity of this material, right? Now let's consider a second material, same vacuum level here, with EC2 and probably a much larger band gap, EV2, EF1. So basically we have a p-type second material and an n-type first material. This kind of a junction is called as a an anisotype heterojunction, where you have a p-type and n-type junction meet each other. If you have an n-type with two materials of n-type meeting each other, it's called as an isotype heterojunction. But here we are using an anisotype heterojunction. So when we have something like this, when they meet, so let me again Q psi S2, and this is Q psi 2, tight, right? And EG2, EG1. So now what happens when both of them join each other? We know that the electrons will go from the n-type to the p-type semiconductor, right? And when the electrons go, it has to bend up, right? And we know that if the conduction band bends up, the valence band also bends to the same extent, right? And we know that if the electrons go to the p-type semiconductor, it has to bend down. Similarly, the bending in the conduction band and the bending in the valence band in material 2 should also be in the same level, right? Now what happens when they meet each other? It has to match, right? So now let's see how to match each other. So now let's consider the situation where we have a heterojunction of two materials with dissimilar electron affinities. So as we discussed previously, let's take a p-n junction. We'll consider two situations where the n side has a higher electron affinity. So that will be the first case 1, where the n side has an higher electron affinity. So higher electron affinity, let's say basically it has a much lower conduction band when comparison to the other, right? That's what higher electron affinity typically means. So we have something like this. The vacuum level is here, and this is EG1, and we discussed this is a case 1 where n side has higher electron affinity, right? So our Fermi level is here, and when the junction is formed, the Fermi levels has to match, right? And now we have the second material with a lower electron affinity, right? And let's say we consider it with a higher band gap. Now this being an n and the other guy being a p-type semiconductor, the conduction band on the n side should bend up, and the other side, this guy should bend down, right? Let me write something like this. And similarly, if the conduction band on this side bends, this guy should also equally bend, and if you see, this guy should bend up. Right? So you can clearly see, because of the fact that these two materials have different band gaps, right, the bending will not match equally, they will not meet, so there will always be a discontinuity, right? And you will have this guy being EV1 minus EV2, or Kelson del EV, and this discontinuity will be del EC, right? Why? This is EC2 minus EC1. Why? Because as we saw previously, electron affinity is a material parameter, right? If this is chi2 and this is chi1 everywhere, at this point it has to meet, so there should obviously be an discontinuity here, right? So because this guy should be chi2 and this guy should be chi1, right? So there is a discontinuity in this position, which is chi2 minus chi1 minus chi2, which will finally turn out to be EC2 minus EC1. So this is the discontinuity in the conduction band. Similarly, you can clearly find out as we follow through. This will be the discontinuity in the valence band will be EV1 minus EV2. Now here there are a few things that we have to note. So this is the band bending on the first material, so we call it psi b1. This is the band bending on the second material, this is psi b2, right? And the barrier for an electron to jump from material 1 to material 2, this is psi b n, is psi b1 plus psi b2 plus del EC by Q, right? And the other way around, psi bp is much more complicated, right? So if you see a hole here, first sees this barrier which is psi b2, right, which is same as whatever it is bending here, it has to be psi b2, but then once it is here, it falls down the trap and then now sees psi b1, right? So the whole barrier is very different from the electron barrier, and which is very hard to calculate, because certain times it might so happen that there will be a whole accumulation here forming a 2D whole gas, and we are not going there yet, right? But I'm just saying that you have a very different barrier for the electron in comparison to the hole when you have a heterojunction, right? Now let's take, so now that we understand how do we draw the band structure for a heterojunction, right? You just the first and the easiest way to go through is to assume that the vacuum levels are continuous, and then the conduction band should have a discontinuity, and the electron affinity values are a material parameters which do not change, right? Now let us consider a second case where here n side has a higher chi or electron affinity. Now I'm going to say the n side has a lower chi, right? Under this situation, let us read out the diagram, right? So we have the same thing here, right? And remember, this guy is going to be a p-type material because we saw the n-type should have a lower psi. So this is our second material, larger band gap, right? Oops. And n meeting with p, and of course this is the vacuum level, right? And this has a higher chi2 is higher than chi1, right? And if you can see, the electron should move from second material to the first material, right? So it will bend up, and this guy should bend down. Obviously here again you can clearly see there should be a discontinuity here, right? Because so this is eventually right. It has to, right? And you can, so this is chi1 and the other one is chi2, right? Now this side should bend up and this guy should bend down, and at the same spot you will have a discontinuity in the valence band as well. And you can, this is del EV and this will be del EC, right? But then now you see that you have a discontinuity in the conduction band here, whereas in the previous case you have a discontinuity in the valence band in this particular form, right? And if you happen that if this dip is very close to the Fermi level, you can clearly see that you will have an electron accumulation here, right, forming a two-dimensional electron gas if you have an n side which has a lower chi. This is the recipe to form discontinuity in the conduction band, giving you a two-dimensional electron gas, and the other side a two-dimensional hole gas, right? So with these ideas, let us see how we can model the current across this particular junction. Obviously, as we saw before, right, wherever there is a band bending, you will have a depletion width, right? You will have a depletion width here, and the current through this can be identified by making a very simple approximation. You neglect these discontinuities and assume that you have a smooth varying potential profile. So what people typically do is they assume that we don't have this but have this kind of a smooth band structure. If you have something like this, then you can use what we have derived previously. Once again, the applied potential V will tell you what is the electron injection, so basically this is the hole injection on this side and the electron injection on the other side, right? So one can actually calculate these numbers, and we are not going to go into the detail right now, but the calculations are pretty straightforward. So the electron, let's go here, right? This is much easier because this is very similar to the PN junction that we previously saw. So when we have something like this, the electron injection here is given by Jn is given by Q dn ni2 square by L n2 na2 e power qv by kt minus 1. So this is quite simply the electron diffusion current through this PN junction, and you know very easily that the minority carriers or the properties of the second material is what is considered when we calculate the current injection from the material 1 to the material 2, right? So this is your I naught, as we discussed previously in the PN junction side as well. Similarly, the whole injection from material 2 to material 1 will depend mostly only on the material properties of the material 1. So Jp will turn out to be Qdp ni1 square by Lp1 nd1 e power qv by kt minus 1. And the total current is obviously the summation of these two, but the most important thing here to note is the actual relation between these two currents. So Jn by Jp is what of interest when we do this heterojunction. So if you divide one by the other, you will get Lp1 dn2 nd1 nc1 nv2. Nc and nv are obviously the effective conduction band and valence band parameters, and of course this came in from ni square, right? dp2 na2 nc, this is 2 nc1 nv1 e power minus eg2 by kt. This is by e power minus eg1 by kt. So finally it will turn out to be approximately equal to nd1 by na2 e power minus del eg by kt. So what it tells is, if we have a PN junction with a heterojunction here, you can determine the ratio of the electron and hole current by the difference in their band gaps. So this is particularly useful when we use an heterojunction bipolar when we are in a bipolar junction transistor, right? Because you want as minimal base injection when compared to the electron injection, right? When we have a homo junction, obviously this is not possible because both of them are pretty similar, and both of them will be similar, will have same values, right? The amount of hole injection of electron injection, and can be only controlled by doping densities. But here, in addition to the doping density, you can also control by just changing the band gaps. So if you have uh, if you have a if you have a positive band gap difference between the two, you can clearly see that you can have a very high electron current in contrast to a very small hole injection in this way. And this is used in a wide band gap emitters. So you typically have a wide band gap emitter and a small band gap base to have what is called an heterojunction bipolar transistor, HBT. Right? So we will stop here on our discussion on heterojunctions. Of course, there are a lot more to learn in these things, and the literature is wide open, and there are many applications in this particular device structure. But in the interest of time, we stop it here. And finally, the next continuation of this section will be a small summary and conclusion of our course, and we will meet you in the end. Thank you.